So I guess most of you have already seen these cars driving around in the Bay Area, especially here. So advancements in the fields of robotics, machine learning, sensors, computer vision, hardware, and this is to name just a few, have played a tremendous role in the ongoing research and development of autonomous vehicles. We have seen substantial interest and research efforts being put into autonomous vehicles and in both academia settings, industry settings, as well as technology companies. But still, there are still a lot of challenges that need to be tackled before autonomous vehicles can be safely and seamlessly integrated within the human environments. So I'll begin first by talking about the standard AV autonomy stack. So usually the typical autonomy stack for an AV is a modular framework. And so you have perception, prediction, planning, and control. So perception is like the eyes of the AV. So it involves sensing the environment via onboard sensors and processing the collected data to understand the world around them. And typical tasks in perception can include like object detection and tracking, classification, to name just a few. The next part of the stack is prediction, which is might already be a spoiler for my title, but I'll be talking mostly about prediction. So the prediction stack then uses the processed data from the perception stack and attempts to predict how the surroundings might evolve, such as predicting the trajectories of other vehicles, for example. Next is the planning stack. So the planning module will determine a safe trajectory to get to the goal that avoids the obstacle along the way. And finally, the controller module will be responsible for determining and executing the desired steering wheel angle and speed command, for example, to follow the planned trajectory. So the benefits of having a modular framework like this is that it's interpretable, generalizable, and reusable. But at the same time, because each subsequent stack depends on the upstream stack, there could be cascading errors. So in our work, we focus on the modular approach, particularly on the perception and prediction part of the stack. So predictions in autonomous vehicles. So prediction capability is essential to the AV system as it allows the AVs to proactively plan safe trajectories based on anticipated human behaviors, thus enabling safe and socially aware autonomous systems. Future motion forecasting in AVs is generally performed in two ways. So the first method is trajectory prediction for each human agent, which is agent-centric types of method. So typically, the agents in the environment, such as pedestrians, vehicles, or cyclists, are first detected and then tracked by the perception systems separately, and then the prediction system will perform trajectory forecasting for each agent. An alternative representation or approach to the agent-centric trajectory prediction is a map-based environment prediction, where the collective occupancy probabilities of the environment, which has been spatially discretized as grid cells, are predicted. So since prediction is done on the discretized grid cells instead of the traffic agents, object detection and tracking is generally not needed. And this added benefit makes occupancy prediction robust to partial object occlusions. So in our work, we'll be focusing on the map-centric approach to prediction. So there are environment prediction challenges, like for example, here. So because humans can be, there's diverse behaviors to humans, there's sometimes that the behavior of humans might not be might be unpredictable and all that. So predicting human behavior is very challenging. And so to tackle these challenges, our thesis will contribute to developing spatiotemporal environment prediction framework that leverage meaningful contextual environment information. Another challenge to environment prediction is that this is very particular to environment-based prediction is that objects tend to vanish at longer prediction time horizon. And so here comes our thesis conclusions. So our contribution will focus on the problems of spatiotemporal environment prediction. In the first work, we propose an end-to-end occupancy prediction module that leverages environment dynamics to predict future occupancy grid maps representations. So our model learns the static and dynamic parts of the environment separately, and it makes a final occupancy predictions of the entire environment. And in our second work, we developed a modular perception and prediction framework to predict the OGM representations in the future of the environment. We introduced a learning-based static dynamic segmentation that is map-centric and similar to the OGMs for seamless integration between the upstream static dynamic segmentation and downstream occupancy prediction module. And our last conclusion is we developed an environment prediction framework that leverages environment semantic information to predict the future OGMs of the environment. All right, so we begin with the first work. So before we talk about spatial temporal prediction, we need to be able to represent the environment. And so a common way to represent the environment is through an occupancy grid maps or OGMs. So OGMs is a map-centric representation of the discretized space. A region in space usually can only be either, can only be either free or occupied. And so in this evidential OGMs representation, the believed masses for each allowable hypothesis, which in this case is occupied, free, or occluded, must sum to unity. And so the benefit is that this type of representation of the environment can distinguish between occlusion and moving objects. And for easier visual interpretability, we can estimate the actual occupancy probabilities through possible transformations, such as we can use picnic stick transformation. And so this figure shows what a typical occupancy grid map might look like, and ranges from 0 to 1. So each cell can be free or occupied. And so we talk about the environment representation. So next part is environment prediction. So in the computer vision community, deep learning has been shown to be very successful in spatio-temporal prediction problems, such as video frame prediction task. And techniques that's based on convolutional long-short-term memory, or CONV for short, are a standard for spatio-temporal or sequential data. And so an example of such models is predictive coding network, or PREDNET, which has been shown to be successful to learn how to predict the future video frames. And since we have seen that the OGM holds structural similarity with the RGB images, prior work done by Ikina et al. Have successfully repurposed the video frame prediction task to predict the future occupancy maps. And therefore, similarly, we also employ this existing PREDNET model in our study as well. So what are some of the prediction challenges to occupancy grid map prediction? So first, moving objects tend to vanish, especially at long time prediction horizon. And secondly, it has been shown that it's very, even though, okay, so there's another representation of OGMs, which is called dynamic OGMs, or dogma for short. So instead of just believed masses that's stored in the OGM, you can also store additional cell-wise velocity estimates. And we would expect that the dynamic OGMs, when used as environment representation to predict the future occupancy grid maps, will perform better than the static OGM where there's no velocity information stored. But it has been found that these two representations perform very similar. And so our research question is that how can we effectively incorporate dynamic information in the environment to improve our OGM prediction accuracy without the need to explicitly estimate the velocity information? And so our contributions are twofold. We developed a double-pronged occupancy prediction model that effectively incorporates environment dynamics and also help to reduce the common issue that arise with the OGM predictions, which is vanishing object. And so with these two challenges in mind, our approach is that we propose to separate the environment into the static parts and the dynamic parts. And we are inspired by this because when humans drive, we usually distinguish between moving and stationary objects, and we tend to pay more attention to the moving objects. And so by this, we hope to bring the focus to moving objects so that the network knows to pay extra attention to these objects. And so by this, we propose to separate the environment into static and dynamic parts, and then we modify the occupancy prediction model, or we modify the planet model that we employ in this to have two different prongs, static and dynamic, and each prong would separately learn to predict the motion models of the static and dynamic environments. And then the output of these two prongs would be the future OGM predictions of the entire environment. So this is our approach. And so the question arises is how do we go about splitting the environment? So we assume that we have object detection and capability in this study. And that means that we have access to tracking IDs across frames and also object bounding boxes. And so when we know the object ID, so we can know the object position between each subsequent time steps. And so we can compare their positions and then classify those objects as static or dynamic. And then after we know the points that are static or dynamic, then we project those points onto what we call binary dynamic mask, where the red here cells here, which are an example of what a vehicle might look like on the occupancy grid map here, as dynamic, and then the rest static. And with those methods in mind, we now know how to split the environment into either static or dynamic by multiplying this mask to the full OGMs. And so if we want the dynamic OGMs or dynamic parts of the environment, then we can just multiply those two together. Otherwise, then we multiply with 1 minus of the dynamic mask. And so here's a recap of our pipeline. So starting from LiDAR sensor measurements, with the assumption that we have object detection and tracking capability, we can then transform or convert the LiDAR sensors into an occupancy grid maps and also the binary dynamic mask. And then these inputs with the dynamic mask will be used to split the OGMs into static or dynamic parts of the environment, and then feed into our occupancy prediction module, and then predict the future OGM predictions. And so in our study, we we construct OGMs from the Waymo open data set, the LiDAR data from the Waymo open data set, and we construct our occupancy grid maps to be 128 by 128 cells with a cell resolution size of 33 centimeters. And so that equates to 42.7 meter by 42.7 meter with the ego vehicle at the center. And what we want to do is to predict the next 15 frames in the future from the observed past 5 frames. So now we go to some qualitative results. So here we can see an example test scene with multiple vehicles driving straight at relatively high speeds. And so this is an example of what an OGM input might look like for 5 frames. So we can see before we go into the predictions, we have ego vehicle at the center, and then these cells represent another neighboring vehicles. And you can see the free space here, and red signifies occupied, and then the green signifies occluded. And so here's the prediction results of those inputs into our occupancy input model. And so we predict the next 15 frames in the future. So this is the ground truth, and this is the result from our works, and then we compare our result with 3 other baselines. And so we can see that our model here retains the vehicles for the entire prediction horizon, which vanishing object tends to be a common problem in OGM prediction. And so and this also happens with the vehicles in front of the ego vehicle as well. And so we go into some quantitative results. So to quantitatively evaluate the prediction performance of the model, we use 3 metrics. So we use the mean square error, the image similarity metric, and what we also have dynamic mean square error, which is just the mean square error, but we only calculate the MSE on the dynamic parts. Yeah. Yeah, and so we can see that our model perform better across than the baselines across all metrics, and the MSE metrics will tell you how it's a measure of how each predicted cell, how each predicted occupancy probability for each cell is compared to the ground truth. And the image similarity metric is a measure of how well the structure of the scene is maintained. And so the takeaways of the occupancy grid map prediction here is that we develop a double-pronged occupancy prediction model that effectively incorporates environment dynamics, and we help with the issue of the reducing vanishing. We help to reduce the vanishing object issue without the need to estimate the velocity information. And so the limitations of the current work is that there's a need to know the static and dynamic objects in the environment in advance, because we use that information to split the occupancy grid maps. And so this means that we need real-time object detection and tracking capability. And so with these 2 limitations in mind, we aim to develop a model that is capable of real-time moving object detection and able to do prediction part of the stack. And so the research version for our second work is that how can we directly integrate the segmentation capability with our OGM Prediction model. And so the contributions to this part is that we developed a learning-based static dynamic segmentation model that directly integrates with occupancy prediction module. And we don't have to assume the detection and tracking capability. And we propose using an occupancy-based environment representation across the entire system to enable direct integration. And with our proposed input representation, we are able to accurately segment static and dynamic objects. And so here's a recap of our occupancy prediction framework in the previous work. So we know that the limitation to generate this binary dynamic mass is that we need object detection and tracking capability. So simply put, we don't want this sort of setup. We want to turn this into something like this. So instead of having that ability, so we want to have a model that can just take the LiDAR sensor measurement and transform it into some form of representation, pass through this model, and we get this binary dynamic mask. So that's our desired model. And so we have a list of things that we want to take into account when we want to design this model. So first, we want to develop this model so that it can be directly integrated with the downstream occupancy prediction module. And so with this in mind, we need to design a map-based environment representation that are compatible with the OGM representation, because that's what the downstream module use. And that representation must also be able to be constructed from the LiDAR sensor measurements as well. Another thing is that because we want to detect moving objects, so we need to consider the temporal domain, and because moving objects signify movement in time, and so we need some sort of information that will let you know that this is moving. And so what we want to do is moving object detection, but just on a map-based representation. And so we just say moving object segmentation task. So there's been a lot of numerous successes with semantic segmentation using deep learning. And recent work by Shen et al. Have adapted semantic segmentation architectures for moving object segmentation tasks. And prior work have also developed a 3D point cloud-based semantic segmentation architecture that also predicts the dynamic objects by using sequential point cloud data. However, an approach that based on operating directly on 3D point cloud data is usually very computationally intensive, as well as and also difficult to train. And so Shen et al. Have successfully adapted range projection-based semantic segmentation architectures for dynamic object segmentation. And they use range images as an intermediate representation of the point cloud. And this is done to reduce the complexity, the computational complexity. It was found that the segmentation performance can be improved by using residual images. And these residual images is just the are just the normalized absolute differences between the ranges of the current range image with past range images. And so following the approach, we also adapt semantic segmentation architecture, specifically Salsa next in our model, which is a range projection-based semantic segmentation architecture to perform dynamic object segmentation, but on our occupancy-based environment representation instead of the range images. And this is done to allow the direct integration between the upstream moving static or dynamic segmentation with the downstream occupancy prediction module. And so we propose using an occupancy-based representation for the static dynamic segmentation model. So there's two representations here. The first is sensor grid map, and the second one is residual grid map. So the sensor grid map just grid maps that reflect the sensor measurements, and they can be generated in the process of converting the point clouds to occupancy grid maps. So each grid cell in the sensor grid map contains the occupancy class instead of the belief of its occupancy probability. And so the occupancy classes include occupied, free, or occluded. The second representation is residual grid map. So we designed the residual grid map such that they represent the changes in the occupancy class for each grid cell between the current and the past time steps. Our aim is to provide cue to the model to pay closer attention to regions where there are changes in the occupancy classes. For example, when they change from from occupied to free or free to occupied. And so these changes are indicative of potentially moving objects. So how can we generate the RGM or the residual grid map? So we derive the RGM by finding the differences between the sensor grids at two different time steps. And we know that both of these SGMs need to be transformed into the synchronous system. The goal here is to have a model that can guide the network on where the dynamic objects could be located at. So when there's a change between the occupancy classes between two time steps, such as changing from free to occupy or occupy to free, which is indicative of potential moving objects, we assign a value of 1 to the residual grid map. And for cells that do not show any change, such as from occupied to just remaining occupied, we just assign the values of 0 to it. And so, for example, if we consider the vehicle here and here, after we compensate for the ego motion of the sensor grid map so they can be in the same frame of reference, the RGM example for these two are the ones circled here. And so we see that when there's a change in classes, there's a flag of 1 here and 0 here and 1 here. And so now the model knows that these two are potentially moving objects, potentially belong to a moving object. And so the model takes this into account and compare with the current sensor grid maps. They can know that, okay, these two represent the change that belongs to this vehicle here. So we finally derived that the model for static dynamic segmentation in this form. So just to recap, we can construct an occupancy-based environmental representations in the form of sensor grid maps and use these two sensor grid maps to construct the residual grid maps. And these two can be used as an input into the static dynamic segmentation model. And then the output of the model would be what we wanted all along, which is the dynamic mass, which tells you what parts of the environment are moving and what parts are static. And so this is the combined modular framework of the two modules. So a quick recap for static dynamic segmentation. We construct RGM from two different sensor grid maps. We arrive at the predicted dynamic mass. And because we want to predict multiple frames in the future from multiple past frames, in this case, we can stack the predicted dynamic mass together and then input it into our occupancy prediction module. And the occupancy grid maps input here can be constructed the same way as what we have done before. And then the final output will be the predicted occupancy grid maps in the future. So here's some results of the first module, which is the static segmentation. So the two columns here are sensor grid maps and virtual grid map. And then the last two columns are the ground truth, dynamic mass, and the predictions that we have from the model. And so we have 3 example scenes here. Vehicles driving in traffic, a vehicle turning at an intersection with 2 pedestrians crossing the street. If you can see, there's like small cells, very small cells here, which are indicative of pedestrians. And also a scene where an illegal vehicle is driving through a busy intersection. And so generally, we can see that our static dynamic segmentation model perform very well when segmenting objects. We know that the moving vehicle tend to have very strong signals in the visual grid map. So you can see that these green cells here, which belongs to potential moving cells, bright. And then, however, when we look at the busy intersection where there's a lot of things going on, there's vehicles going everywhere, and then all the smaller cells here represent walking pedestrians. And so we can see that generally, we also perform well when segment these moving objects. However, for very slow vehicles or small objects like pedestrians, because they tend to show up as very small in the sensor grid maps and also in the visual grid maps, the signal is very weak for these 2 types. And so these very slow vehicles or pedestrians, the model tends to have a harder time segmenting them. However, if even there's a relatively weaker signals, the models can still pick up. But in the case of like partial object occlusion, say, or when there's no signal at all in the visual grid maps, then the model might miss them completely. And so this is the result from the second part of the module. So similarly, an example test scene. So we have an input, which is the task OGMs, task 5 frames, and then we also have predicted dynamic mass from the upstream module. And so these 2 as an input feed into the occupancy prediction module, and we get these predictions. And similarly, we compare our method across 3 other video frame prediction architectures that have already been repurposed to predict occupancy grid maps. And we can see that our model still maintains moving objects appearances for longer in the prediction comparisons. So we calculate the same metrics as before, MSC, dynamic MSC, and image similarity, and we arrive at this result. Our models perform better than other 3 models. However, they perform relatively similar to one baseline model. So when we compare the current result with what we had before, and this is based on using the same training data and test data, we see that there's still the previous model where we actually have access to ground truth object detection and tracking data. So our models perform based on a predicted dynamic mass, and so the model that has actual ground truth as input will represent an upper bound or lower bound in this case, because lower is better. However, the relative performance is quite similar. Okay, so the takeaways here is that we've developed a learning-based static dynamic segmentation model to determine static and dynamic parts of the environment without the need for object detection and tracking information. And we can directly integrate the segmentation module with the occupancy prediction module using our proposed occupancy-based representation, which is the sensor group maps and the virtual group map. So the limitations of the current work is that there's the accuracy of the prediction will rely on the accuracy of the static dynamic segmentation module, which is common for modular approach because what we see will be a result of what the upstream module can predict. Another limitation is that we can miss very slow vehicles and pedestrians when there's no signal in the residual group maps. And so we have seen how the occupancy prediction module can successfully use the environment dynamics in terms of static and dynamic parts in the environment. And that helps to improve the prediction accuracy. So with that in mind, we would like to know if we can now incorporate environment semantic information within the occupancy prediction model so that the model can leverage environment semantics to further improve the prediction accuracy. So our hypothesis is that if the model receives semantic level information, it should be encouraged to learn the differences between different object classes and then improve the prediction accuracy. For example, pedestrians or cyclists class should move slower than very fast moving vehicles. And so that semantics information, we hope, would help with the prediction. So our contributions are twofold. So we developed a method that incorporates semantic information to the occupancy grid map prediction framework. And we propose an environment semantic representation that are compatible with occupancy grid maps. So before we go into how we can incorporate environment semantic information, we will first look at the occupancy prediction model. So the PredNet model that we employ in the occupancy prediction is a video frame prediction architecture. And generally, the RSTM or convolutional long short-term memory is very good with learning structure in the spatial temporal data. And so here we can see that the representation layer here will be responsible for learning the dynamics in the data. And in the PredNet model, we have the representation layer here, and we have the prediction layer and the target layer and the error between these two layers. And the target layer here is actually the occupancy grid at the next time step, because that's what we want to predict. And so in PredNet module, this module can be stacked on top of each other. And so you have a series of these stacked modules to help learn the spatial temporal structure in the data. And so for semantic environment representation, so to incorporate the semantic information, we propose representing the environment semantics in the form of semantic grid maps, or SMGMs here. The SMGM represents the same local environment space as around the ego vehicle as the OGMs and carry cell-wise object level information. And so the SMGMs can be constructed in a similar way to the OGMs by assigning the cell corresponding to sensor measurements with its respective object level. So in order to obtain the required object labels, we use salsa mix architecture to perform semantic segmentation before generating the SMGX. And so a related work here. So while the video frame prediction task, which is predicting the raw RGB pixel values, has been widely studied, the task of predicting the future semantic segmentation maps of future video frames was just recently introduced. And Luke et al. Found that it is better to predict future frames in the semantic space instead of predicting future video frames and then perform semantic segmentation on those RGB space. And so, inspired by their findings, we modified the predictive model architecture for video frame prediction to predict the future environment semantics in the form of SMGMs that we have proposed. And our aim here is to provide the occupancy prediction model with the future semantic information via the predicted SMGMs, thereby allowing the network to better model the dynamics between different object types in the environment. So here's our modified occupancy grid map prediction with Semantics Model. So within this model, we can input the semantic maps and then the occupancy grid maps. The semantic maps will first go through a semantic prediction model, which is the repurpose the predicate. Instead of predicting future real frames, we propose it to predict future semantic maps instead. And then the output would be the predicted semantic maps. And we have seen previously that the recurrent representation layer here is responsible for learning the spatiotemporal structure. And so we want to feed this into the representation layer within the occupancy prediction model, with the hope that the semantic information here would be learned in representation layer in the occupancy prediction as well. And so according to this diagram, so we have an input occupancy grid map and got feeds in, and then with the semantic information introduced directly into the representation layer, the output of the model would be the predicted occupancy grid maps. And so here's some results with the predictions with environment semantics information. So we have an input similar structure, an input of past 5 frames of both the semantic maps and the occupancy maps. And we want to predict the occupancy predictions of future frames. And so we can see here that our method performed better than the baselines. And because now we are working with environment semantics, we choose the baseline to be just pure occupancy information, and then occupancy with dynamics, and then ours should be occupancy with semantics. So we can see the relative performance between the 3 approaches. And then here's another example scene where a vehicle is making a turn at the intersection. So this is the vehicle we interested in, and based on these 5 inputs, we can somewhat see it's approaching a turn, but it's very hard to know if we don't actually see the camera images. So with these inputs, this is the prediction result. So the ground truth shows that the vehicle is making a turn, and our method shows that the predicted occupancy, it shows that it's mostly heading straight. So failing to make a turn in the predictions, but we still retain the appearance of the objects for longer in the prediction horizon compared to when they run here. And so here's the quantitative results. We can see that the occupancy with semantics perform significantly better than the occupancy plus dynamics and just pure occupancy. The dynamic MSE is around 1.72. I know I'm saying the number, but we can see that the relatively superior performance could be attributed to the model actually know what the object it is seeing, what type of object it is. And so the takeaways here is that we develop an occupancy prediction model that leverages environment semantics, and that helps to improve the prediction performance via the cell-wide semantic level information to help retain the appearance of the moving objects for longer. And the limitations of the current model is that we need semantic segmentation capability. And the model can get computationally intensive depending on the number of semantic labels that we want to use in our model. So in our case, we use 12 semantic labels, which ranges from vehicles, pedestrians, cyclists, buildings, road, curbs, and etc. And so if you want to increase more semantic labels, that will get more computationally intensive. And so that's the limitation that can be addressed. And so to summarize, in the first work, we developed a double-pronged occupancy prediction module to predict the spatiotemporal evolution of the environment while leveraging environment dynamics. And the second work addressed the limitations of the first model that assumes the need for detection and tracking capability by incorporating static dynamic segmentation module within the modular framework. And so we've developed a dynamics-aware spatiotemporal environment prediction. And then the third work predicts the occupancy grid maps in the future while leveraging the semantics information instead of the dynamics information. And this is for the hope that the model will learn to predict motions better if the model knows what it is seeing. And so with all this in mind, we want to develop models that understand what it is seeing. So we want to help guide the models with this useful information. So future directions. So apart from the limitations in the semantics work that we have seen that we could address, we can incorporate sort of a hybrid agent-centric and map-centric prediction systems. So for example, we can develop a occupancy prediction framework that also incorporate the trajectory prediction. And so this is, for example, one useful case might be that if you want to predict further away, or if you want to have a bigger area of prediction, the grid maps will scale with the size of the area we want. And so that can get really big real quick, but the number of agents does not necessarily scale with space. And so it might be useful to have sort of a hybrid representation where we predict the agent's trajectory further away from the ego vehicle while retaining the occupancy grid maps predictions for the entire environment instead of the agent near the ego vehicle. And so that's also coming to play with another future direction where where the problem is scalable trajectory prediction in very dense urban settings, where we might have like hundreds of agents in the scene, and it's very hard to keep track of every agent. And so if we combine both the map-centric, say occupancy grid maps with the trajectory prediction, and so we can use the maps prediction to help with the trajectory prediction without the need to keep track of a lot of agents. And another promising future direction is the multimodal environment prediction. So we have seen in the example test result that the model failed to predict a turn in the intersection. And because based on the past inputs, going straight is also one valid prediction, because in the input we see that it seems that the vehicle is going straight. And so if we have a model that can predict different outputs, then that could be useful in the prediction and the downstream planning algorithms. And so these are my references.